All right, 2.1. So this is a new module. You'll need to remember that you need to have finished everything in Module 1, which would include the quiz that goes along with Module 1. Now, let us start. This is for systems of equations, by the way, substitution and elimination. There are two different methods for solving systems, but you'll have to keep in mind that usually on exams they will specify which method you should use, and you then have to use that method. Okay, and that is department policy, so there's nothing I can do about that. So you need to have both of these down by the end of this lesson. So a system of equations, it just tells us that there's, in this case, we're looking at two equations, so we're not actually worried about triples, which would include another axis, which we're not worried about. But we're looking right now, at least for 2.1, at two different values, both x's and then y's. So what we're going to see is equations that make straight lines, such as this one. Okay, now that's not straight, but I did the best that I could. And then perhaps you may see a line like this one. That's okay. Now, the solution to this system that I've just created randomly is the ordered pair where the lines intersect. And I can see they intersect at this point, which appears to me to be at 5, -2. Okay, so this also means that in the two equations that are given, this ordered pair would make both of them true. So a solution to a system of equations will make both equations true. And we can even check that, right, when we go through this work. But you have to check on both. Now, here's what a non-solution is. Sometimes you may find that you use the wrong ordered pair, such as this one. This would be 6, -4. Okay, but you can see how 6, -4 is on the red line here, but not on the purple line. If you thought that 6, -4 was the solution, you would plug it into the red equation and you'd see, hey, that's a true statement, so it is the solution. It is a solution. But you would find when you put it into the purple line equation that it would give you a false statement. This red point here would give you a false statement for this one because it's not actually on that line. So it would not be the solution. And the same thing would be on for any other point on this purple line other than where they actually do intersect. Also think about any other random point such as this one. I guess, you know what, I'm going to change it to this one. This would be -4, -3. So if you said, hey, you know what, the ordered pair that makes this, that is the solution to this system is -4, -3. See how it's not on either the red or the purple line? It means that if you were to try these two values into the original two equations, either one, you'd find that both are false. Okay, but again, the actual solution here in green that I put, it would, whatever the equations are for these, would make both of them true. And that's the key point there. You can check your answers in this section by plugging the values that you get for the solution, whatever you think it is, back into the equations, both equations, okay? And then you can check to see if it gives you true statements on both, because that's what an equal sign is, right? It's conditional. If you found in the end that, like we've seen before, maybe 1 = 2, that would be a false statement. We don't want false statements. We want true statements. So here's the process that we use for solving systems of equations with either elimination or addition, which again, you may have to have one, you need to have both of these down specifically and know how to use them exactly. So if it says, hey, you got to use elimination to solve this, we need both equations in the same form. Okay, so we can't have one in slope-intercept form and then one in standard form. And even if it were in standard form, like let's say like 3x - 2y = 5. Now let's say we had, again, it's just some other random equation, but let's say we had 4y plus 6x = 18, something like this. Well, the problem with this one is that we need the x's and the y's to line up, and this one is technically standard form. So I personally would just switch where the x and the 6x and the 4y are, and I would rewrite this one as 6x plus 4y equals 18. Then I could go from there to determine which variable I want to eliminate. So that's the first thing we got to do. We got to make sure they're in the same format, and so I'll show you that I would do that, right? Put that purple equation, I would show it as 6x plus 4y. Now from there, we got to multiply one of the equations, or at least sometimes both. We got to multiply one or both equations so that we have matching coefficients of either the x's or y's. What this means is that we're choosing a variable to eliminate. Now that takes some analysis at first. It's going to save you some time if you can just sit and think about which one would be easier to eliminate. Now if I were to look at this one, which is just a randomly created system of equations, I would say right away that I would probably eliminate the y's. Well, why is it? It's because we need the coefficients to be opposites. Well, yeah, opposites. That's actually technically the term we want. So like here I have -2 and +4, so I can see I have opposites already. All I've got to do is make the 2 match the 4. So I wouldn't have to do anything with the purple equation. I can multiply the red equation by 2. Then I would have a -4y here and a +4y, so that when I add them, that's why it's called addition as well, it would eliminate the y's and I'd be left with x's. Now I'm not going to do it right now, but so that's what you do. You got to multiply the equation or equations by some value so that the coefficients of the same variable match, or they're opposites. They're matching opposites. Isn't that better? And then you add the two equations together, which you can do. What this does is it creates a new equation, which would then help you, but it's eliminated in this case, the one that I was doing. It would eliminate the y's. It allows me to solve for the x's, and then I have an x value. That's solving for just the one unknown from the new equation that's obtained. After I have that x value here, I can go back to either one of these. I replace the x in either one with the value that we find, and then I solve for the other variable, which in this case would be y. Okay, so and then I substitute the value from step 4 back into one of the original equations, solve for the other unknown. Yes. So you solve for either x, then y, or you solve for y, then x. Sometimes students just skip these two steps. They forget to solve for the other variable, and unfortunately that is only worth about half credit, even though you're really more than halfway there because you don't need the system necessarily to solve. Okay, so then at the very end, you go back to the original equations, both original equations, and you replace the x's and y's in there just to make sure that you get a true statement. If you don't get a true statement, then you're in a situation like we saw in the graphs, right? You may find one that's true and one that's not. It means that the ordered pair you have is on one of the lines, but not both. It has to be on both in order to be the solution. So we need true statements out of both. So the first thing I'm going to have to do is change these in the same format. I like this x minus y1 because that's what we call standard form. So I'm actually going to change the order of this one just by switching the location of the x and y. So it's now -2x plus y equals 9. And then the top one is showing 5x minus 3y equals -23. So at this point, we look and we say, is there a variable usually, because we're looking to eliminate it, can we get rid of a variable pretty quickly? And there is one that we can get rid of fairly easily, though possibly not quickly, is the y's. The reason why that is because the coefficient of this y is it's a phantom 1. That's going to allow me to just multiply that by anything that I want, because I want the coefficients of y's to be opposites. So I can see this coefficient of y is negative, this one's positive, but this being a 1 is going to make this a lot easier to match the 3 than it would to make the 5 match the 2 or the 2 the 5. So I'm sticking with the y's here, and I'm going to take that second equation there, and I'm going to multiply all the terms. You have to multiply all the terms, otherwise you've changed the actual value of the equation, which we don't want. We just want to change the way it looks without changing the value. I've got to take that 3 and I've got to distribute it into this set of parentheses. So I start here. I can see I've got 3 times the -2x, which is -6x. Now, if we've done this correct, when I distribute the 3 to the 1y, I should end up with +3y because that's opposite to -3y, and then they should eliminate. And yes, 3 times 1y's would give me positive 3y's. And then finally, 3 times 9 is 27. So that top equation, we didn't do anything with it. We were just forcing the y's to match or be opposites. And they do. They are now opposites. So you can see negative 3y plus 3y. Now elimination is also known as addition. So I'm going to take all 3 of these terms, which they need to be combined with like terms. When I add these together, it's going to give me a new equation, but without y's, because 5x plus negative 6x would be negative 1x, and negative 3y plus 3y, that does actually zero out. It eliminates. And then negative 28 plus 27 is, I guess I see negative 1 here. And the last thing I need to do to solve this one is simply take both sides, divide by negative 1, which will make the x value, or the x coefficient, positive 1, which we want. Negative 1 divided by negative 1 is also positive 1. I'm going to make that a phantom one so it looks pretty. So the other thing about this, that's an x value that equals 1. That's the x value in the ordered pair that would make both equations a true statement, right? Where x is 1. Now, not only does this mean that you should write this in a ordered pair format, which actually sometimes on the assignment it may say, what's the x value, what's the y value? Just please, on a test, because this happens more often than I wish it did. On a test, make sure that you don't forget to solve for this y value. You need it. So we are going to solve for it. And I'm going to use the second equation because it's just y by itself. I wouldn't have to worry about a principle of equality to get rid of that negative 3. So I go back to again, I want to use one of the original equations. Y minus 2x equals 9. But right here, from the value we found, we're pretty sure that x is 1. So in solving for this, I'd say, well, negative 2 times 1 is negative 2. I now have y minus 2 equals 9. And then one final principle of equality will do this by adding 2 to both sides. That will zero this out. And then I can see that y equals 9 plus 2, I guess, is 11 there. So our ordered pair should be 1, 11. Now we can check, right? So what is 11 minus 2 times 1? It is 9, okay? But we have to go to the other equation. We have to say, well, what about 5x minus 3y equals negative 23? Will that give us a true statement? As it turns out, it looks like it will. Let's replace the x and the y. If I'm wrong here, that's fine. We can fix it if we need to. But the x value is 1. The y value is 11. Okay, so working this out, 5 times 1 is 5. 3 times 11 is 33, or negative 33. So 5 minus 33 should equal negative 23. And what do we get? We get a false statement out of this. This is going to be negative 28, not negative 23. So we got to go back and find where I made a mistake, and that's okay that I made a mistake. I can see it. It was simply copying down. I thought I copied this negative 23 down as negative 28. I need to go back and fix that, okay? In fact, that means I need to fix a couple other things. Okay, so this, let's fix that then. So instead of that being negative 28, it was negative 23. And negative 23 plus 27, that would have been positive 4. 4 divided by negative 1, though. That process still remains. So x should be negative 4. So let's fix that, okay? And let's come back over here. We went next to over here. So this would be negative 4. So that would have made this negative 8. So we should have added, oh, that would have been positive 8, though. So we would have subtracted 8 here and subtracted 8 there, and that would have just left us with an individual 1. So that's okay. We can fix that 1 there. Let's go back over here, though, and see what happens to these values when we replace them. So right here, we're pretty sure x is negative 4, so let's fix that 1. And now the y value, though, is 1. So let's see what we get. 5 times negative 4 is negative 20. Negative 3 times 1 would be negative 3. And negative 20 minus 3 is negative 23. So here I can see, finally, even after making the mistake, which was not on purpose, that I have a true statement. So it makes this equation true. And we can do this just in our heads pretty much. That would have been 1 minus 2 times negative 4. So 2 times -4 would have been -8. 1 minus -8 would have been 9. Yes, that still works. And we just checked the top equation. So both are true. And now I know for sure that I have in fact found the solution to our system of equations. So here's a new system. We're going to use elimination or addition to solve it. We can see that the format is the same. It's an x term, y term equals some number. X term, y term equals some number. So the format is the same. We don't have to switch the format like we did on that last one. But even before we start choosing which variable to eliminate, what I want to do is see if there's one that's going to be easier than the others. Now in doing so, I see something unique happening. But I can see that -18 and 9 should work. Same with -6 and 12. And so it doesn't really matter which one I eliminate. They probably are about the same. So on that last problem, I chose to eliminate the y's. This time I will choose to eliminate the x's. I can see that they're already opposites. I got a +9, -18. So they should eliminate. I just need them to match now. So, and also the other good thing is 18 is a multiple of 9. So I can just take the equation that has the 9x and just multiply it by 2, which is going to force the x's to be opposites. So I'm going to show that. Okay, so I'm not changing the overall value of the equation. I'm just changing the way it looks. But I have to distribute this 2 into all 3 terms there. So 2 times 9x is 18x. Now before I move forward, again, the 18x was part of the plan because 18x positive is opposite to -18x. So when I combine these two, they should eliminate. Next, 2 times -6y would be -12y. And then 2 times -15 would be -30. And if you need help with these calculations, please use your calculator. So let's look at, let's copy this other equation now. -18x plus 12y equals +30, right? Well, we see these. We are now ready to add them together. So let's do that. The 18x's minus 18x, that zeroes out. That eliminates just as we planned. But then we have -12y plus 12y. That's going to be 0y's. And I'm showing the 0y because I would like to see what it's going to equal. -30 plus 30 is also 0. Now let's stop here, okay? Because we don't actually have to do any more. What I find from this is that I got 0y equals 0. As it turns out, and I would ask you really to think about this, is there something you can multiply by 0 to get 0? Now this may take some thought. It may take you some time to remember some of those old rules. But anything multiplied by 0 is 0. So what I've just written there, it's telling us that it doesn't matter what you replace y with, you're always going to get 0. And what we see here is that the statement here tells us that the equation will always be true. That's for any y value, okay? So, since the y values are always going to be true, the corresponding x values will also be true. Now, of course, you'd need them. But this is also telling us then that essentially the two equations, the two original equations, are the same equation, which tells us then that there are infinite solutions. There we go. And that's actually something you may have to remember, okay? So the answer to this one is actually infinite solutions. Okay, and that's all we'd need to say. And why is there infinite solutions? Because if you were to graph these, you would end up with the same line. It's one line that's on top of another. And so remember, the solutions to a system is where the two lines meet, but the two lines would meet everywhere. They have infinite intersections, and so there's just infinite solutions. We don't have to actually find any one specific solution. All we have to say is that there are infinite solutions. Now that's a pretty unique scenario. We won't always see those unique scenarios, just like we saw with the first example. looks like this one also will produce a different example, okay? Now this one, just some analysis, okay? Again, some analysis may help us save some time. Right now, I'm telling you I'm going to eliminate the x's, and here's why. It's because the coefficient of that first x is just a 1. It's a phantom 1. And I can make that 1 easily a -7, and I want it to be a -7, not positive, because this is already +7. I can make it a -1 quickly because multiplying by 1 is easy. The 2 and 5, yeah, that's not as easy, okay? Now that's what I would do normally, but I'm going to purposely do this one. I'm going to eliminate the y's on purpose, just in case you didn't notice that you could just force that coefficient of x to be -7. Okay, so I'm going to do this pretty much the long way, although you will get the same answers if you choose to eliminate the x's first. Okay, so what I would do here is actually just to make the coefficients match, right? Because I'm looking at 5 is not a multiple of 2, so I can't multiply by this one and get 5 easily. So what I'm going to do, kind of like it's very similar to what I would do with common denominators. I'm going to take the top equation and simply multiply it by the coefficient of the y, because I'm choosing to eliminate the y's. I have to multiply by that coefficient in this top equation. So this is going to give me, again, I got to distribute to all the terms. That'd be 5x. 5 times 2y would be positive 10y. And then 5 times 5 is 25. Now, in the second equation here, I am going to multiply it by 2 because that's the coefficient of the y in the other equation. But I need them to be opposites, and right now they have the same sign. So I'm going to multiply it actually by -2. So this will give me a new equation there. So -2 times 7x's is -14x's. -2 times 5y. This is a key one, so we have to pay attention. It's going to give me -10y. And I can see, before I continue, I can see that these will eliminate. And then -2 times 26 would be -52. Now I am ready to add these two equations together, and this will eliminate the y's. I can see that it will create a 0y there. 5x's minus 14x's. That would be -9x's, which is equal to 25 minus 52, which is -27. Okay, so it's going to come out very pretty. So one principle of equality, all we got to do is divide both sides by -9. And I can see this 1x, x is going to equal -27 divided by -9 is +3. So just real quick, as a reminder, don't forget to make this an ordered pair. I just found the x value, which is 3, so I'm going to fill that in. All right, now I got to go back and I got to say which of these equations am I going to use to solve for y. I'm going to use the top one just because it looks easier. Is it actually easier? Probably not. But it doesn't matter. You should get the same y value no matter which of the two equations you use. And again, that happens because it needs to make both of the equations true, right? The ordered pair, that is the solution to the system. It's the intersection of the two lines, so it needs to make both of these true. I just found the x value, so I'm going to replace that x with 3, and I'm going to solve this equation. So let's get started here. So I'm going to get rid of that 3. So subtract 3 from both sides. That's going to zero that out. Drop my 2y, which now equals 2. Okay, so I can see by dividing both sides by 2 here, that's going to make my coefficient of y a phantom 1. 2 divided by 2 is 1. And we end up with the ordered pair 3, 1. So I'm going to go back to both equations and check. Okay, so I'm not going to show the work here because we want the calculator to do that for us. But if I replace, in fact, you know what, I will. I'm going to show both equations, right? So I got x plus 2y equals 5. And then we have 7x plus 5y equals 26, right? But I know the x's, they should be 3's, and we should get true statements. So there's a 3, and there's a 3. And then the y values are 1's, which we need to replace both of them. And here I am just checking for truthfulness. So there's my question mark, okay? And again, this is just something you'd put into the calculator. But I can see here 3 plus 2 times 1 is 5, and 5 does equal 5. That's a true statement. Okay, what about the other one? 7 times 3 is 21, plus 5 times 1 is 5. 21 plus 5 is 26. And so I see here also 26 equals 26, which is a true statement. Okay, so that's true as well. We see that both are true, and now I feel a lot more comfortable saying, hey, look, I can box these in knowing for sure. I did the checking. I used the calculator. I know for sure that 3, 1 is the solution to this system, which again, it means that's the ordered pair where the two lines come together. All right, for this one, we can see that the two equations are not in the same format, so we need them to be in the same format, right? So we're going to force them to become the same format. So the first equation there, we can see that it has the x term, then the y term. Right, there's the 2x, there's the y, there's the number. The other one has the y term equals the number and then the x term. We can't have that. They need to be in the same format. So I'm going to change the bottom one into the bottom equation into the format for the top one. So I'm just going to add 6x's to both sides. Of course, I'm not going to combine the 3y with the 6x. I'm going to keep them separated, which would give me 6x plus 3y equals negative 17. So I didn't line up the equal signs exactly with that line that came down, but it still works. So we're going to look at the other equation as well. I should probably just rewrite it. So that was 2x plus y equals negative 6. And from here we need to do some analysis, right? What coefficient can we make opposites and make them pretty quick? As it turns out, both y's and x's would work. For this one, though, I'm going to force the coefficient of x there to be a negative 6. Now, I want it to be negative because the 6x above it is positive. So I'm gonna multiply this by negative 3. So again, the 2 multiplied by negative 3 is going to be negative 6. They'll be opposites, and they should eliminate, right? So let's go ahead and distribute that negative 3 into the full equation. It has to distribute it to all the terms. So negative 3 times 2x would be negative 6x. Negative 3 times 1y would be negative 3y's. And then negative 3 times negative 6 would be positive 18. So that equals positive 18. The top equation we're just going to rewrite. So that was 6x plus 3y equals negative 17. Now you'll see in doing what we have done, in just choosing to eliminate the x's there, it's also going to eliminate the y's there as well. So let's just show it though. So we're going to add both equations together. It does eliminate the x's as we have planned. We have to add all the terms. 6x plus negative 6x zeroes out just as planned. But we see 3y plus negative 3y is 0y's. I need to see that because anything times 0 needs to be 0. But we see here that negative 17 plus 18 is 1. Well, I can't think of anything that I can multiply by 0 to get 1. I mean, there is actually, but I'm not going to, okay? So what we end up with here is there isn't anything that we can multiply, at least for now, by 0 in order to get 1. What this tells us then is that there actually is no solutions, which to me is a good thing because it takes away the need to do any more work right here. We actually are just pretty much done. So the other thing that this tells us, which hopefully may be helpful for you, is that since there are no solutions, it tells us that the equations created by the two, or I should rewrite that. The lines, if we were to graph these, the lines created from the two equations would be parallel and never, I'll emphasize that, never intersect. So in other words, these two lines, they have a lot in common, the slopes, but they never meet, which is kind of tragic. All other lines, though, they will meet once and then drift apart forever, which is also kind of tragic. What the heck? Little nerd joke in there for you guys. But no solutions is really what we're looking for in this one, and that completes this problem. So what you're looking for no solutions is if you ever choose to eliminate, you'll see that you get like 0y equals not 0. Like we saw in the example 2, 2 examples ago, if you get 0y equals 0, that's always true. But anything times 0, if it equals not 0, it's automatically no solutions. So next we have solving a system with substitution. So what we're going to do is if it's needed, we'll manipulate the equation so that one variable is on its own side of the equal sign, and it should have a coefficient that is 1, phantom 1. Then we'll determine what one of the variables equals that expression, and then we'll replace the variable in the other expression with the one that is given, or the one that we've made. So at this point now, once you've done that, you will only have one variable in the equation. You just solve for that one variable. Once you get it, you replace that value into the other one of the 2 equations and then solve for the final unknown. Finally, you're going to want to check your answers on these. So for one like this, here's what I'm going to do. I'm going to take this equation, which represents y, or that expression, and I'm going to take this y here, and I'm going to replace it with this expression. So that y now equals, just as it shows above, negative 2x plus 93. Now you'll notice that I just did that because it was already showing y equals something. I didn't have to manipulate it, so it's just y equals something. It was already there for me. But then we still have the rest of it, right? So this is going to equal 10/3 x minus 147. And so from here, I'm just going to solve this like I would a regular equation, right? Principles of equality. I'm going to do 2 principles of equality in 1. I want all the variables on the left, so I'm going to subtract 93 from both sides to start. Okay, I can drop my equal sign, but negative 147 minus 93. Let's see, that'd be 0, carry the 1, 5, and 4, 240. A negative 240, thank you. And then negative 10/3 x, we're going to zero that out as well, or the 10/3 x, by subtracting 10/3 x, that's better. So negative 2 minus 10/3 x, and that's going to be, looks like negative 16/3. So from here, what we're going to do is take the coefficient, negative 16/3, and simply divide it by itself. What this is going to do is it's going to make a phantom 1x equaling, but we got to do the negative 240 divided by the negative 16/3 as well. And this should complete the process for us in solving, at least just for the x. Remember, we still need to solve for the y. Please never forget to solve for the y's. So in my calculator, I'm even using the fraction button there. Looks like it gives me 45. So that's kind of a big number. It doesn't matter how big it is. Okay, so expect some of these numbers to be big, but I can see my x value is 45. Now I go to either one of the equations. I'm going to choose the top one just because it doesn't have any fractions in it. So y equals negative 2x plus 93. And I'm going to replace the x with 45. The 45 that we found, right? So when I solve this, it's going to give me a y value. And I can just put this into the calculator. So negative 2 times 45 is 90 plus 93. Sorry, negative 90 plus 93, which is just a positive 3. So 45/3, right? This should work. We pretty much already checked the top one. Negative 2 times 45 plus 93 is positive 3. But how about the other one? Well, that would have been y equals 10/3 x minus 147. Now, if we've done this correct, we should get a true statement if we replace the x with 45 first, and then also the y value with the y value that we've already found, which was a y value that's 3. So I'm just going to put this in the calculator. 10/3 times 45 minus 147 equals 3, and we get a true statement. So both equations are true when we replace the x with 45 and when we replace the y value with 3. Therefore, we know that that is actually our solution. All right, here we're going to solve this system of equations. This one's already set up for us. It's pretty nice, okay? And what I mean by that is that it tells us what x is right there. So what I'm going to do is I'm going to take the x, which is negative 2y plus 5, and I'm going to take the other equation, okay? So I'm going to rewrite it just so I have a little bit more space. but it's 7x plus 5y equals 26. You'll notice that in doing this, I've given myself a lot of space between the 7x and the plus 5. That's because I'm replacing this x right now with the expression that x equals, which is negative 2y plus 5. And this is the equation that I'm solving. When I do this, when I finish solving it, I will have the y value, which then I can solve for the x value. So I got to distribute the 7. 7 times negative 2y, which would be negative 14y's. 7 times 5 is positive 35. I do better 3. And then plus 5y equals 26. So now I got to combine my like terms. Negative 14y's and 5y's would be negative 9y's. Still drop the positive 35 there, and this still equals 26. But a new principle of equality here to get rid of the 35, so minus 35 from both sides. Drop the negative 9y, and this now equals negative 9. Last of all, we'll divide both sides by negative 9, which will make the coefficient of y a phantom 1. Y equals 1. Negative 9 divided by negative 9 is actually 1, and we have just found the y value there, right? So I found the y value. It is 1. So now I'm going to go back to the second equation there, or the first equation rather, which is x equals negative 2y plus 5. And I'm going to replace the y value with the y value that we found, which is 1, and that's also a pretty easy number to work with, right? So I just plug this into the calculator. It will tell me that x equals 3. So I now have the ordered pair 3, 1. That confirms the top equation. I still need to confirm the bottom equation though, right? So I'm going to go to 7x plus 5y needs to equal 26. It needs to equal 26 if it is actually the solution. And so I'm going to replace the two values we have. The x is 3, and the y value is 1. Okay, so is this true? So question mark over the equal sign. So I don't know if it's true, but I see 7 times 3 is 21. 5 times 1 is positive 5. Will this actually equal 26? Well, it does. 21 plus 25 is 26, which, for now at least, equals 26. That's a true statement. And so we get a true statement. And now we know for sure that we have actually found the solution. It made both equations true, which means they intersect. If we were to graph them, they would intersect at the ordered pair 3, 1. So there's some substitution. But now, on this one, it says, hey, look, if you were to solve these equations, which one would be better? Well, if we ever see equations organized in this standard type form, I know it's a y term, x term equals a constant, but it's practically in standard form. Both of them are. That tells us that if we see that, chances are we're going to want to use elimination for that. And so we'll say, yeah, if you see this type of equation, you'll want to use elimination. Now, pretty much by the process of elimination, we could say, well, the next one you'd use substitution. But it's more than that, okay? It's more because you can see the second equation show what y is as an expression, which would allow me to replace this y with this expression. I'm not going to solve it. You could if you wanted to, either one or both. But I just want you to know if you see y equals or x equals some stuff, then you should know that you should use substitution.